So thank you. Found it amusing that Gene talked about genes, and now Danny should talk about deduplication. I guess I have very nice buzzwords up there, and so deduplication and cloud, these are major buzzwords. I'm pretty sure everybody in the room has heard about clouds, used clouds, played with clouds. I'm not sure about deduplication. It's a big buzzword, but it's a niche buzzword. So I'm going to dive into the deduplication part and tell you a bit about it. So here we go. What is deduplication? Well, you pretty much hear it in the name. You have duplicates and you want to deduplicate, remove them. So storing only a single copy of redundant data. And it can be applied for files, it can be applied for blocks. There's a whole plethora of ways to do deduplication, but the basic idea is you don't want to store so much data, you really want to save on space. And this has become a major theme in storage because storage is just outrageously growing fast. Major savings have been seen especially in backup applications. So deduplication has been very big in that area of backup. It's becoming more prominent in other places as well, moving to primary data and such. I think showing an idea or a theme is impactful. Can be done quite easily by looking at the amount of money spent on it. So many big companies spent lots of big dollars on companies that did deduplication. That would be an indication that something good is happening there. So these are acquisitions that happen. There's been more work done on this recently and more companies working on these recently, but this is a start. So that was kind of what is deduplication. How is deduplication done? So I said blocks and files. I'm going to go with files to the rest of the talk, but if you feel uncomfortable, just do the translation in your words. So how are files deduplicated? You don't go and say, let's look at two files and really compare them. So for each file that comes in, we're going to hash its content, the actual content of the file. It's done usually with the cryptographic hash functions for very good reasons. SHA-1, SHA-256 are popular candidates for this. And now you're going to store a big index containing all of the hashes of the files that you have in your entire system. And now when a new file comes along, it's pretty simple. First, calculate the hash of this new file. Look it up in the index. Now, if it's new, add it to the index and store the file. If it's old, the index should have a pointer to where the file with this content has previously been stored. And now you're storing a pointer rather than a new file. And wow, you saved a lot of space up there. So this is the basics deduplication. It's very simple. Deduplication is very good for saving space. It's also used for saving bandwidth. It's another place. Actually, it's probably the more expensive resource out of the two is bandwidth rather than storage. So how do you save bandwidth? Using what is called client-side deduplication or one deduplication, source-based deduplication. You hear these words around. It does the following. So the client computes the hash on its side. It doesn't send the file over like we did before, but some client on one side computes the hash of his function, sends first only the hash to the other side. Now the storage server on the other side is going to look at the hash, check the index, and do well, if it's already there, it can just store a pointer as it did before. If it's not there, it should reply to the client and said, okay, this is new to me, please send the file over. And then the file is sent. If the file is redundant, we saved on the bandwidth, which is big. in some cases. So this is client-side deduplication. And now the third one, the other thing we had up there is security. So deduplication and security, or privacy in this case, is an issue. And we've shown it's an issue in two works that I'll go over in this presentation. And it's relevant to the following setting. It's a setting that you have client-side deduplication that I just defined a second ago. And you also have cross-user deduplication, meaning if two or more users store the same file, it's going to be deduplicated. So we are trying to save globally. It's not just a per-user thing. And so this is the setting of interest to us. And, well, is it interesting to other people as well would be the next question rather than just ourselves. And this is where the cloud buzzword finally comes in. Cloud storage and deduplication have been a good match, and mainly because the cloud in the storage world has been very successful and popular in the backup applications. So backup and synchronization is a huge market out there. I think most of you have used all sorts of backups for cloud, or all sorts of meaning of moving files through the cloud. And here files tend to repeat themselves quite a bit. So there's really lots to gain from deduplication. I've listed at least 3 companies that either use currently or have used cross-user and client-side deduplication. These are not small companies. This is Mozy, which was a big acquisition of EMC. Dropbox, that I think most of you are familiar with. MemoPal was a big file sharing backup application in the European countries. There's more. They don't usually go out and say, hey, we're using client-side deduplication, so I can't give you the full list. But for these, I know for a fact that at least at some point of time, they have been using this methodology. Another one, an interesting one, is MP3 Tunes. This one we do know that have been using deduplication extensively, and we know it because they got into a lot of legal trouble. Really, it wasn't a coincidence that in the example I had the song Let It Be. I mean, a really good place to do deduplication is music services, because people tend to hear the same music over and over again and store the same files. And now there's a big legal question. If you're storing music for Yuval and for Alon and for Eyal and for, I mean, I'm saving their music. Am I allowed to store a single copy for all 3 of them? Because they all paid for the music. They're not thieves. They're very, I'm missing the English word. אנשים מהוגנים. Honest. Mehuganim, honest, decent, yes, thank you. Very decent people, they don't rip off music, but am I allowed to store a single copy for 3 licenses? And this went to court, and actually I think the last ruling was that you're allowed to store a single copy. This company was sitting in the courts because they were doing deduplication on cross-user files in their services. Okay. For anything that has copyright issues. So it could be software, it could be movies, music, anything with copyright. It's questionable whether you're allowed to dedupe or not to dedupe because of copyright issues. Okay, so that was kind of a side note, but a nice one. So let's get back to the privacy issue. So I think I've established that it is a phenomena out there, and now what do we have? So this is the first work that I've done together with Benny Pinkas and Alex Shulman-Peleg, and the point is this: when you have client-side cross-user deduplication, you get a sort of a peephole into other people's data. It's a very small peephole, but it exists there. It works as follows. I can actually tell if someone has already uploaded a file to the system. It's narrow, but it's existent. And what can you do with this peephole? I mean, there's a bunch of attacks that we discussed. One is searching for illegal content. I mean, a government that knows that some illegal content is out there can check whether it has been stored at a cloud provider. And now it can go and subpoena, get a subpoena from court, forcing the cloud provider to open up the privacy promises to their customers and show them whoever owns this illegal data. That's one way of taking advantage of these people. Another one is a salary attack. If you're looking at, it's called a salary attack because you can have, say, a small document that only says, okay, hi, Danny Harnik, this is your salary, and there it is. And it's just this standard form. Another person can come and upload this form with just go over all the possible salaries that jumps over $100 until he hits the right one. And then he'll notice that deduplication has occurred because he's uploading a file and he's getting an answer, oh, this file already exists in our system. So he just found out what my salary is. There's another one that we have, some covert channel. Benny Pinkas actually implemented this sort of game with a student of his. What he do is he'll give you a disk on key with some images of playing cards, and then say, okay, please pick a card and just store it on your laptop, and then synchronize with your Mozy backup that you have on your laptop or your Dropbox or anything. And then after a couple of minutes, he'll come back and say, okay, this is the card you picked. So it's kind of this neat card trick that you can do using this peephole. Several ways to really get over, kind of mitigate this issue. One would be just encrypt everything you're putting out there, and then you know nobody's seeing what, because there's not going to be any deduplication out there. It so happens that the companies doing this deduplication do not like you encrypting the data because they don't gain anything from deduplication. It also is just a fact of life. People do not like to encrypt their data when they upload it to the cloud. Applications will not do it for them, or so forth. So that's an option, but it really blocks out a lot of other things you can get from the cloud. You can do deduplication at the server side only, but I just said that bandwidth is a big resource in these services, so probably not a good idea. You can deduplicate only long file. This was actually implemented by Mozy files after we notified them of this work. And it's pretty nice because a lot of the meaner attacks can be done only on small files. And you don't gain so much by saving on small files. You gain on the big files. So you only deduplicate client-side the big files. You can deduplicate server-side the small ones. And then we came up with another idea that says, okay, let's do this noisy deduplication, or a randomized process that decides whether you duplicate or you do not deduplicate. And this really goes to employ some of the techniques that we know from privacy in databases, there's a whole field of privacy that says, well, if a lot of people have the file, then leaking this information out doesn't really matter. If it's just one person having that file, then it matters. And then you can kind of not deduplicate at times and make the whole distinction of how many files exactly are out there and how many are not, make it a fuzzy line. So you'll only start deduplicating after enough people have uploaded this same file to the cloud. That's the basic idea. I'm not going to focus on this work, so I went over it pretty quickly, but you're invited to look it up, Google up the paper, and you'll find more. So what next? So we have another work on deduplication and privacy, same setting, but it's a more direct attack. This one was with Shai Halevi as well. It's more a direct attack in the sense that you'll see soon, because you actually get data out of the cloud. But it starts with the following theme. Suppose I get hold of a hash of your file. That's how it's going to start out. So here's the attack. The attacker obtains a hash of the victim's file. I have a file. Somebody managed to get the hash of this file. Now the attacker is going to sign up to the storage service, the cloud service, and do the following. It's going to upload a file, some file, any file, and rather than sending the hash that it calculated on this file, it swaps it with the hash that it stole away from me. And now it sends the request over to the cloud. The cloud should be familiar with this hash because I gave it. I mean, it was my file. It's up there. And now the cloud is going to say, well, OK, I know this. I've just registered this file. You don't have to send it over. I've just registered this file under the name of the attacker. Now the attacker is a legitimate owner of the same data in my file. And he can download it freely, no restrictions in the downloading, and he got my file away. So this is really a way of taking a small 160 bits and relaying this into the whole file. And nobody is, I mean, this is a cryptographic hash. It's strong enough so there won't be any collisions out there. So you can't even find collisions if you're maliciously trying to find collisions. So no two files in this service will have the same hash. Once you've sent out the hash, that's sort of proof that you have the file on your side, and that's enough for the cloud to actually register it on your name. And this is really the problem here. So we have really a small hash representing a big file. What can we do about it? So first, I'm going to say a few words about justifying this attack as a real one. So I put in red two things, which are the non-trivial parts of this attack. The non-trivial parts are mainly the attacker obtains the victim's hash. How does he do that? Is this really a threat? And the other one is, well, how do you do this swapping right here? This is some software you got from the vendor. You're going to have to hack into that. How hard is that? Whatever. So I'm going to have one slide on each of these and go forward. Obtaining the hash. So we have a number of things to worry about. One is, well, the hash isn't really supposed to be secret. The hash itself tells you nothing about the file unless you actually know the file in advance. So it's not meant to be secret. People say, well, in the same sense, you can steal my secret key and get all my data. But secret key is something that is supposed to be kept secret. Have you ever tried retrieving the password that you have just forgotten out of your laptop? That's a tough thing to do because the passwords are kept privately in a secure way. these hashes are not kept privately. Actually, looking into the code of one of these big vendors, they just have on your laptop a big file. Well, it's a small file. It's a file containing all of the hashes of all of the files that you have out there in the clear. It's not supposed to be kept secret. So the hash is not meant to be a secret. Maybe you can just get it from some other place. Well, maybe you're using it as a checksum or something like that. That's point number one. Two is malicious software. If you have some sort of malicious software in your machine, well, it has access to your data, but for malicious software, sending lots of data out is tough. Sending just a few bits, 160 bits of information outside, there's many ways to do that. One is the covert channel that I mentioned in the previous work, but there's many ways. 160 bits is really easy to send out. So if you have a malicious software and you have a good gatekeeper on the network, not allowing to send big chunks outside through the network, still you can send just a bit and get all the data through the cloud. A third one is what we call the Cdn attack. It says the following. Suppose Alice wants to share a file with a friend. So Alice will do the following. It'll upload this large movie to the cloud service and sends a hash over to all of its friends. So it's sending just a bit of information to its friend. It's not using up all its bandwidth that is limited on her little Palm Pilot or an iPad, whatever. And then the cloud is used, so now you can, each and every one of their friends can download the file from the cloud using just the hash. It imitates uploading and then it downloads it back. Why is this problematic? Because these clouds typically are not meant to serve as a content distribution network, which is actually what Alice is doing here. Also, there's no real good way of tracking privacy issues. So this is an issue. I'll say a few words more on the Cdn attack in the next slide. So how about swapping the hash that I mentioned? How hard is it to re-engineer this? So it turns out to be not that hard. I mentioned the work that Benny did with the student, Leo Dorendorf. There's an implementation called Dropship. Somebody wrote a code that works on Dropbox and actually implements the Cdn attack that I just mentioned. Now, you would think that this would not be problematic because Dropbox is a file sharing service. So why should it matter that someone is doing file sharing over the file sharing service? It turns out it did matter to them. It was kind of being sold as this is some torrent. It's an alternative to using torrent. And Dropbox actually went a long way to legally force this guy to remove this code from the web because they were afraid of piratic downloads going via this way that they have absolutely no control of. So this was problematic for Dropbox. They actually went out of their way to remove this thing. There was another paper also attacking Dropbox on this. And I'll say that there are upcoming standards for cloud storage that really want to implement client-side deduplication. So everything is out open there. You can swap hashes easily. So it's a non-issue now. One last word kind of on the whole story is that Dropbox has actually, because of all these attacks, this Dropship, the 2 or 3 papers that came out, they decided eventually to stop doing client-side deduplication altogether. It was really bad for their PR. So solely based on deduplication, client-side deduplication attacks. Okay, solutions. So we really want to mitigate this attack. And I'm going to run through a few naive solutions and then get to our solution. So let's start really with a naive one. I said, well, maybe you're using this hash for other stuff. Well, don't. Use a specialized hash. You can take a hash and add this special service name at the beginning, and now it's a non-standard hash, so it shouldn't really leak out. The problem is that the way to compute this hash should be on every client, on every side. Everybody has to know this, otherwise you don't get client-side deduplication. So for the Cdn attacks, for example, or malicious software, this does nothing. This doesn't change the game at all for them. So let's try a bit harder. Let's use a challenge response here. So instead of using one hash every time, let's say I want to upload a file. I'll tell the cloud. The cloud will return to me with a challenge and say, hash your file with this random number. And now I can only create the hash with this random number if I actually know the file. So it forces the client to actually have the file in order to be able to answer this challenge. This is problematic from another sense. So it's very secure. It's problematic from the sense that the cloud, in order to verify this, it also has to have the file. Now the cloud has the file. That's not the point. The point is that the cloud now has to go and compute the hash of the file. It has to actually retrieve the file from secondary storage, disk typically, and go and compute the hash. This is way too expensive for someone whose entire purpose here is to save resources. So this would not work in a practical setting. It's secure enough, but not practical. Alternatively, well, maybe you can just pre-compute a number of these hashes with challenges, store them on a very fast storage, and then the cloud doesn't have to do all this work. And that's pretty good as well, only the fact we're getting back to square one. Because if the number of challenges is small, then we're back to the root cause that there's a short representation of the number of hash challenges that really represents the whole file. So we're back to the root cause, and we haven't solved that. Okay, so what we propose is what we call proofs of ownership. It's a process that goes as follows. The server is allowed to do some pre-processing on the first upload of the file and store a bit of information. This has to be very small, few bytes, that it can access for every upload of this file. And now there's a proof stage. The proof stage is only done on upload. It's not when downloading. You only do this when you're uploading a new file. And you're uploading, and it has been identified that there is deduplication client-side. So it will go as follows. I come to the cloud. Here are the hash of the file that I want to upload. The cloud says, OK, I'm familiar with this one. Prove to me that you have this file. Here is a challenge. Compute the challenge on this file, but the cloud should be able to verify the challenge based solely on this small pre-processed information. So this must be bandwidth sufficient, because the whole point is to save bandwidth. And the client computation also cannot be too long, because, again, resources are the main cause here. So we don't want to slow down the whole process. Time and memory is a big deal here. And now security definition. What are we trying to secure against? So suppose we have a malicious client, and we really went out to cover all the bases. So this is stronger than what most people would intend, but this is what we work for. We aimed at. So we have the file, and suppose the file is actually, it has some inherent knowledge to its structure which is known. So there's partial knowledge of the file, like the header or stuff like that. This is, well, the way to formalize it is saying, well, there's some unknown portion of it, there's entropy to the file. So there's prior knowledge, and there's at least k min entropy to this file. And then we're also trying to prevent against these CDN attacks. So you can also get from an accomplice m additional bits. So accomplice data. And this is not really bits about the file. You're getting some computation about the file from an accomplice. And if both of these are still leave some unknown quantity about the file, bigger than a security parameter, then there's no way to answer the challenge, to actually get the challenge right. One point to mention is the additional information from accomplice is pre-computed. So it's not a man-in-the-middle attack. I don't send the challenge and then have you go ask your accomplice. That's no problem. He'll just answer the response to the challenge. So you get some previous knowledge, you get some accomplice data, and then you play on from there. This is the security definition. One short remark is there's a concept known as proofs of retrievability, which sounds very familiar to what we've been doing now. So these are, again, we have a cloud, we have someone proving to the other one that it actually has a file. Only in proofs of retrievability, it's the other way around. The cloud is proving to the user that it has its file. It's actually storing the file. And this role reversal has very big implications to what you can actually do here. So state-of-the-art solutions for proofs of retrievability have pre-processing stage on the file, which is not allowed in our setting, which make them actually not useful at all for proofs of ownership. I'll say this, that proofs of retrievability that do not have any pre-processing are good proofs of ownership. And actually, the first one that I'll show is both a proof of retrievability and a proof of ownership based on a Merkle tree. So first solution. The first attempt goes as following. Here is the file. The pre-processing will do the following. Compute a Merkle tree on this file, and the information stored by the server is just the root of the Merkle tree. For those unfamiliar with Merkle trees, it's a construction that allows to verify that someone's file is actually what it's said to be. And the way to challenge here is say, I'm asking about t locations in the file, t random locations, and the guy the prover is going to send to me passes to the root of values in the file. And here the server, who is the verifier, can actually recompute this whole pass, get the value at the root, and compare it to what it had in store. If this is correct, then everything is done. The proof is actually shows that if a client knows only a p fraction of the file, it cannot succeed with probability better than p to the t. This is nice. It's very efficient, but there's a problem here. The problem is, what if p isn't so great? I mean, what if the guy on the other side knows 90% of the file? And now it wants to prove something, so it has a probability of p to the t. Because we're trying to be very efficient, t is going to be on the order of 10, perhaps, 10 challenges. So 90% to the 10th, that adds up to 35%, more or less. So a malicious guy knowing 90% of the file can actually cheat with probability 35%. That's too bad. It's not as strong as we want. And there's a simple trick to overcome this that was done in proofs of retrievability. It says the following. rather than run over the file, have the Merkle tree over the file, first do some erasure coding of the file, and then do the Merkle tree on the file itself, on the erasure coding of the file. This solves everything out. I'm not going to go into why it works, but it has some very intuitive explanation to it. So this really saved the situation, and now this is a very secure proof of ownership. But what problems do we run into now? So what about this encoding? Is it efficient enough? And the answer is no. So the error correction codes, the erasure correction codes that we are looking at have to pay in one of two things: either have a very large memory or run multiple disk accesses to location in the file. So for a large file, this is going to be a bad solution. Simply because the client is going to work too hard for it. It's really going to affect performance. Okay, so what now? So we said, okay, we don't have a good solution that runs with both little accesses to the file and small space. So let's give something up. And we're really relaxing our security definition here. We're saying, let's have the solution use only an L byte buffer for the computation. Something that, let's say, 64 megabytes. That's pretty big, but it's easy on any personal computer or probably any handheld device as well. But it's much smaller than the actual file sizes. And then we relax our security guarantees. We can only tolerate L bytes of accomplice data. This is the trade-off. So the new definition will look like this. There's this boundary L. You can have all the prior knowledge that you want. You can get your accomplice data, but as long as the accomplice data is less than L, and you still have some entropy about the file left, there's no way you can cheat the proof of ownership. Okay, so this is the new relaxed definition that we work with, and we have a solution for this. We take the file, we first reduce it into this small buffer, and this is going to be supposed to be pretty efficient. So we do this first reduction. You don't use as much memory as before. And now run the Merkle tree on the reduced buffer. And we can prove that this is secure when you're using pairwise independent hashing, which is a pretty simple solution. But is it efficient enough? And the answer is no, not for practical applications. So theoretically speaking, it all looks good, but practical applications, well, suppose the file size is M and the buffer size is L. The reducer that we had requires M times L computations, and that's too much. We want to really push it to M plus L. So time complexity has hurt us here, so we're doing another relaxation, and we're becoming pretty heuristic now. We don't have a good provable code. What we're doing now is, and this is something that we really implemented, and I'll show some graphs on results. So this is now turning to the engineering part of the talk. We run a reducer, but this reducer is doing something very simple. It's just taking locations in the files and XORing a constant number, say 4 locations of the file. Each output byte, which is in the reduced file, is just an XOR of 4 locations in the original file. This is very efficient. But this does not give us the sort of security or the sort of mixing properties we wanted from our error corrections structures. So what we do is we run a mixer on this. We start doing this operation over and over again on the reduced files and mixing things up. We did some tests on how many mixes you actually have, and now you have a reduced and mixed file, and you run the Merkle tree on that. And now the hypothesis, or what we prove, is that suppose this reduce and mix actually forms a good error correction, erasure code. And speaking to coding expert, this does look like a sound hypothesis. There's no proof to it, but it does look like a sound hypothesis. Then security defined against what we call general block fixing sources. We can prove a security claim on this construction with respect to proofs of ownership the way we wanted them. So we've worked quite a bit here, and this is really engineering to give something that both runs fast enough but really covers some meaningful security definition. So the security definition, I really didn't spell it out because it becomes messier and messier, but at least from our standpoint, it does mean something to real life. These block fixing sources are meaningful, and the hypothesis, I'm pretty comfortable with it. Okay, let's see performance evaluation. So now we really went engineering, so we have to give some numbers as to how fast this can actually work. And what we'll see is, well, there's the time it takes to read something from the disk. That'll be this pink thing. There's the time it takes to actually compute the SHA on this file. And then you have the overheads of the reducing, the mixing, and the Merkle tree on top. We see that for smaller files, the overhead is pretty big. But for bigger files, it becomes more on the order of actually computing the hash function. So is it really worth doing? And this is a tricky question because it depends. What is your data? Is there deduplication in your data? If there's no duplication in your data, don't bother with the whole construction and everything. It really doesn't make sense. And then also you're trying to save bandwidth. So what is the speed of the line that you're working at? And we have two lines, 4 lines, 2 sets of lines. One set, the 2 on the top, talk about 5 megabytes per second upload line, which is actually makes sense in, or at least did a year and a half ago when we did this. This is upload, not download. So the 30 megabytes that you're getting now from hot don't count. But what we see is that you're better off doing deduplications with the proof of ownership that we presented. And this is assuming a 2-to-1 deduplication ratio, which is pretty reasonable. And this is for any file size. So as the files grow, it becomes more and more apparent that you're better off doing this proofs of ownership than actually running. So we have the dedupe with proof of ownership is always lower. And now if you're taking a 100 megabytes per second line, everything becomes faster. Still, I think once you're reaching the 0.5 megabyte file, it already becomes faster to work with proof of ownership. For larger files, for sure. So that's about it. As a summary, we identified some security issues that come with this client-side deduplication. It's really being used out there, so it's meaningful. And we introduced these proofs of ownership that are supposed to make this client-side. We look at it as an enabler for the technology because For people who really care about security, you cannot do the client-side deduplication freely. And the challenge was, A, to make the proof meaningful in terms of security definition, but to actually engineer it to run on a real system.